lecture number 4. Hope you are enjoying your time here. So yesterday the lecture was a little bit more mathematical. It's not difficult, but was a lot of math, yeah. And so today we have something more relaxing, okay, which is introduction to models in epidemiology, okay, modeling infectious disease epidemics. And I would call it a gentle introduction, something like this will not be so mathematical and so on. And, just for you to have a notion that modeling epidemics is like modeling populations. It's like a population that has a structure. Okay? So, but before we start with our models, let's go through some history about important epidemics in the world. And while we're going through some historical cases, we can learn some characteristics of important epidemics that historically, and things that we want to be present in our models. Our models have to be compatible with some patterns that we will see looking at the history of epidemics in the world. And also, as a byproduct, looking at epidemics and how things were discovered and science advanced. It's also an opportunity to make an appraisal of the importance of science for society and for humanity. It's something that is at this point important also because a lot of people are attacking scientific methods and so on in society. So, we will go through some history, then have models, and lots of models. Right? So, let us look at this. This is called the Plague of Athens. This was a disease. It's called plague, but actually it was not plague technically. Right? It's called plague in the latter sense, meaning of plague. And this raged in Athens in 430 before current era. During the Peloponnese War, it was one of the first epidemics that has been described by someone. It was described by Thucydides, a historian. And 1/3 of the population died. 1/3, which is high. Even the famous Pericles died. Nobody knows what actually this epidemic was. Okay? So archaeologists try to get some insight on this, looking at trying to find cemeteries of the time and so on. Apparently, it was not plague. It's consistent with typhus, and so this is one of the first reported epidemics. But here we have one thing, okay? It is obviously a very deadly disease, but it didn't kill everybody, okay? So, okay. And second, there was obviously no treatment, yes? Okay? After some time, the disease disappeared, right? So that's important to know, okay? So we don't know if, we can have two hypotheses here. Everybody caught the disease, but only 1/3 died of it. Or we can also say maybe not everybody caught the disease, okay? There are two hypotheses. But somehow, the disease disappeared. Well, obviously then we have even a modeling exercise on plague, the real plague, the bubonic plague. And this is an infection which is caused by a bacterium which is called Yersinia pestis, and can be bubonic, pneumonic, and septicemic. Essentially, it is very deadly disease, and in high proportion, it can be it's deadly in high proportions. But well, today there's an effective method to treat this. It's a bacterium, just penicillin or something similar. Okay. Here, this is curious because plague has been probably the most important disease in the history of humanity. We have had 3 pandemics. Pandemics is usually worldwide, but I mean, not necessarily the whole world. Okay, large extinctions. Okay, so you got the plague of, which are important cases, the plague of Justinian, which is in 541, spreading from Constantinople and killing 25% of Mediterranean population. It's just a very large number. The so-called Black Death, 1/3 of the European population. And third pandemic, which is at the end of in the middle of the 19th century, began in China and spread to India, and was the last great pandemic. Why was it the last one? So here, the plague it's a good example of how science works also. So, first thing is, well, what is a disease? Right? So this is something that for us now, it's an obvious thing. Okay, diseases are bacteria, virus, and all of this. Yeah, well, but you should remember that only in the middle of 19th century, we discovered mainly through Pasteur, that diseases are microscopic organisms, microscopic beasts that are living beings that enter into your body and make you gives you the disease. Right? So it's obviously something that has roughly not even 200 years ago, okay, 150, 160. So this is really, when you imagine what was life before that and how was treatment before that, it's completely different. And the plague was one case of of very intense dispute. Why? Before we have really the workings of Pasteur, this means applying scientific methods to study diseases, we had two schools of people that, well, people didn't know exactly what the disease was, but there was a discussion how it is transmitted. And there were two schools. The one is called the school of Contagionism. So I think disease spread through contact, okay? So through contagion, which is what we say, okay. Oh. But then there was another school, which is the miasma school. It's like that, well, the disease spread through the air. Somehow there's a kind of essence of the disease that goes in the air, and the air is bad, and in this way it spreads from one person to the other. Okay. So now we would say, okay, but this is we know that this is not true. Okay, yeah, but well, this was very important because plague offered a very difficult case for the contagionist school, because plague, there's no contact between infected people. So where is the contagion? Okay, so there was a guy that said that dies of plague here, and then somebody who had no contact with him dies also. How? If you have no idea of the nature of diseases, it is microbe germs, right? Little beasts in your blood. So if you don't know this, then you have a problem in explaining the case of plague. Okay? So this was a very strong and historical dispute. Right? So only after knowing that diseases come to the so-called germ theory of diseases. And in the 19th century, then a lot of people went on to try to discover what's called the etiological agents of a disease. People began to discover what was cholera, tuberculosis, all of this is like the end of the 19th century. Everything has, and well, plague took quite a long time. It's only in the 1880s, which is during the epidemic in China and in Southeastern Asia and India. And it was a guy that is called Yersin, Alexander Yersin, a French person, and working for the Pasteur Institute, but they had some missions in the region that discovered that the agent of plague was a bacterium, which was named after him, Yersinia pestis. So, well, but then there was a problem. Okay, the problem was, okay, how is this bacterium transmitted? Because I know it's a bacterium, okay, but penicillin is only effective, discovered in the 1920s, but effective as a treatment only in 1950. Okay, so at the time, okay, it's a bacterium. What? So what? Okay, what do I do with a bacterium? So there was the case. So what was the transmission route? The transmission route for plague is complicated. Right? So Yersin could establish one thing. He knew that the fact, which was a kind of popular knowledge, was that before the arrival of cholera in an epidemic in a given city, a lot of rats died. You had kind of epidemics in rats followed by epidemics in humans. So he thought maybe the rats also have plague. So he went in and he could determine that actually, yeah, rats also had the same bacterium as the humans. Okay, this was on form. So the rat maybe has something to do with the story. So then another guy, also working for the Pasteur Institute, his name is Simon, Paul-Louis Simon. This guy was working in India actually, and so this guy discovered that the flea is in the story. Okay, that you have a route which goes not directly from the rat to the persons, but there's a mediator. Okay, so once he discovers this. And this is exceptional discovery. He made an experiment to demonstrate this. I don't go into the details, but it's an experiment with rats and fleas and so on. So real experiment that demonstrates this route. And this is maybe the most important scientific results of that time, because this says you something very important. Okay, you need sanitation. You need not to be in contact with rats and fleas. This is enough to avoid an epidemic of plague. Right? This is interesting. So this is already a result. Right? And and finally, this didn't give you any way of, once a person has plague, how to treat the person. Okay? But in 1950, with penicillin and so on, the problem of plague was solved, and we don't have any more plague epidemics in the world. So this is really should be told to people that science can do very interesting things. Right? Millions of people died of plague, and this is really coming from the basic science to the applied things, and in kind of 1 century from Pasteur to Fleming, lots of diseases have been dominated and been not eradicated, but are not anymore epidemic. Just to mention, if you look at the table of the main causes of death at the beginning of the 20th century, like at the turn of the century, there was tuberculosis, malaria, lots of infectious diseases. And if you look now, 1 century later, that's not anymore the case. Now the main cases are cardiovascular problems, things that are not epidemic, are not infectious diseases. Only infectious diseases that are important as causes of death. Any death is important, but if you look numerically on the proportions, and you have malaria still is a problem, and this is mainly due to problems of malaria in Africa. Okay? And HIV. But still, you see, it's much less infectious diseases are important now than before. For the case of plague, here you have plague in Brazil, for instance. You see that there was no known cases after 2000. But the day before, last week there was 1 case. There's a point here that is 1 case in Rio de Janeiro, which is curious. It means that the disease is circulating still. There is the bacterium there. It's not eradicated. And you could ask yourself, sorry, is there plague in the world? So is there endemic plague? So there is still, okay, it's not big problem. I mean, it's not an epidemic, but there are endemic regions. And this is mainly in the United States and US and desertic areas of Arizona and New Mexico, Texas, this part of the country. And in Kazakhstan. Kazakhstan is also a desertic region, and then there you have more cases there. Yeah. And the third main epidemic, the main disease that I would like to mention is the so-called Spanish flu. And actually, Spanish flu is just a name, which is a mistake. This had nothing to do with Spain. Okay. And it's influenza, very deadly strain of influenza. It lasted only more or less 1 year, 1 year and a half, and attained almost all regions of the world. Okay. Even here in São Paulo, first death occurred on October 21st, and at the end of November there was extinction locally of influenza. So again, this is a point that we would like to keep in our mind. There was no treatment for influenza. There's nothing. So actually, what happens is that the disease comes and goes away, okay, without any measures, any treatment, because there's no treatment. It's just so. Let's keep this in mind. So, okay, let's go for the mathematical modeling of diseases, of epidemics of diseases. And so the approach is we will take the population of human populations. We're talking about infectious disease of humans. I will make some commentaries later about infectious diseases for animals, okay? It's a little bit different. And so let's make some assumptions that the population is kind of well mixed. Everybody can be in touch with everybody. We say, okay, but that's not true, blah, 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 but wow. Okay, let's start simple. And it's more or less homogeneous in space, so we don't want to take into account the spatial aspects. Like, okay, there's a number of cases here, but not here. What's the difference between the two places? Usually it has to do with the environment, so space would be non-homogeneous in this case, but well, we don't want to look at this. We want to look at the whole population of, say, a city or locality, and we want to know, model the epidemic in this, in the population. And our approach is we will classify people in 3 classes. So a person can be susceptible, a person can be infectious or infected. At this point, we can use this interchangeably. Okay, a person is infected means it's also infectious. Sometimes for certain diseases, this is not true. The person can be infected, but it's not infectious. Okay? So this is a refinement that can be done. And after some, then there's a new class of recovered. Okay? And here there's, could be also dead, but most of cases we are thinking about removed or recovered. Okay? So, usually people in epidemic modeling like to draw this box diagram, say, okay, S goes to, from susceptible you go to infectious through a contact with an infectious individual, and after sometimes infectious gets recovered, and this is the simplest case. Okay, this is called an SIR model, and we will now build this model. Okay, This is the simple thing. This works well for some certain. First, this is directly transmitted diseases. We are not talking about vector-borne diseases or waterborne diseases or whatever. There's no intermediate agent. And it is like, this works well for measles, smallpox, this kind of disease, influenza. Well, so I divide the population in these classes, and I now want to know how the number of individuals in these classes varies in time. How is the time dependence of S, I, and R populations? Okay, they are functions of time. And we will assume that the population is constant. So S plus I plus R is the total number of, is constant. Is this a good idea? In general, yes, but actually this has to do with the following. Take, for instance, influenza. The Spanish flu case, I mentioned that it took more or less 1 month, a little bit more than 1 month, for between the first case and the last case in the city of São Paulo back into 1918. So it took more or less 1 month, okay? So on the scale, typical scale of the epidemic is 1 month. Okay? Now the scale where the population has a varies, the change of the size of the population during 1 month is almost nothing. Okay? Unless you have a very, very deadly disease and the disease changes the thing. But in general, populations will have changes which are important on periods of many years. Okay? So any disease that is being modeled on time scales of months, okay, then you could say, okay, now we can take the population to be constant. Okay, the two main cases where you should not do this is if the population, if the disease is such that it can really change to a large extent the population, okay, through induces death, or if the disease has a very long time scale. The epidemic occurs over time scales of, say, 10 years and so on. This would be a case where maybe you should take into account that population can be variable. Okay? Can somebody tell me one example of disease that has a very long time scale? No, tuberculosis, usually epidemics of tuberculosis. But I mean, if you have an epidemic of tuberculosis, it usually has a certain restricted time for the epidemic to come and go. Okay, it's true that it goes to an endemic. Okay, it goes to an endemic state. Usually, the endemic state is a small part of the population. But if you look for the epidemic, the arrival and the end, although settling to an endemic state, this is not so long. AIDS. So HIV, it's really long epidemic curve. Okay, so the number increases and decreases on a very long time scale. Yeah? Maybe you should take into account population variation. Yeah? So now let's go through some equation about this. So Okay, this is just what I mentioned about the constant of. So the first equation we want to write is that the time variation of the number of susceptibles should be such that it has to be proportional to the number of susceptibles, but the ratio should be such that the time variation should be proportional also to the number of infectives. Okay, if there's no infective, there's no way of having time variation. Okay, if there is no susceptible, obviously, then this is also true. And this has to be negative, and there's a proportionality constant. Okay? This is the infection rate, or this is the first equation. Okay? Now we will want to also write something for GI dt and GR dt. Okay? But before we do this, we have to pay attention to this guy here. Say you're modeling population an epidemic of, say, influenza, common flu, maybe. Okay, so does the characteristics of this epidemic, like typically how long it takes for, I mean, it increases, decreases, the time scale, and so on, and the infectivity, number of people, the proportion of people that has been infected in a certain place. Does it depend on the size? Let's think about cities. Does it depend on the size of the city? So you have a big city here in São Paulo, with all the areas almost 20 million. Okay? So is it different here from, say, a small city of 10,000 persons? Or not? What do you guess? Yeah, well, this is very particular for flu, okay. But, yeah, but other diseases would not be in this case. So, well, first approximation, the characteristics of an epidemic do not depend on the size of the population, okay. So, the typical time time scale of a population will be the same here or in a city with 1 million persons or 5,000 persons. It's more or less the same. And the fraction of people infected will be more or less the same on all these cities. But this means that here we could have a problem. So let's analyze this here. Let us say that S can be written as the total number of the population times the fraction of individuals that are susceptible. N is constant. This is a function of T. Yeah? And all the other guys can also be written in this. You can consider fractions. Okay? So this is the frequency of susceptibles, of infected, and of recovered individuals. Okay? And if you plug this into the equations there, you would have n times ds dt is equal to r minus r times n squared times s of t I of t. These are the frequencies. So you get this here, you get this here, you get ds dt is equal to minus r n s times I, which says that the epidemic depends explicitly on the population size. Okay? Bad. Should not. Okay? You see, this is proportional to the rate of change of the number of individuals. Okay? So epidemic would progress much more quickly in a large population than in a small population. So the fraction of people getting infected per unit time, or I mean getting, which is this here, would depend proportionally to R. So that's against the common observation we have in human societies. Okay? This means that a way out of this is saying this guy R has to be a function of n proportional to 1 over n. So usually we will write R is equal to the beta divided by n. Beta is the new infection rate, per capita rate. And so you have this, and then in this case, obviously you are okay. You will get this thing here, this way, where in principle this beta does not depend on n. Okay, that's what we call here making the model frequency dependent. Okay. You see that these equations, when I took this into account, depend only on the frequencies of susceptible and infected individuals. Okay, so only the proportions come in, not the total number. Right? I will continue to write this in the way I'm writing, but keep in mind that there is a beta. This is 1 over n. Okay, when is this important? When I want to compare different localities with different number of people and so on. So you have to more or less remember that this is 1 over n here. Okay. Well, very good. So you could ask yourself, why is this so? Why does the population size why is the population size not important to describe the dynamics of the epidemic, in this simple case at least? Why should this be so? And first, and when is it not true? Any guess? Hmm? Mm-hmm. Hmm? Yeah, this is true. So, but what we are saying here is actually is at the point of view not of the population but of the individual, it's the rate of infectious interactions with other people that will actually be somehow in this guy beta. Okay, there are more recent advances in epidemiology that actually calculate beta from the network of interactions between people. Okay, that's a topic connecting network theory with epidemiology. But the point is, the number of interactions that you have in a city of 10,000 and a city of 1 million is more or less the same. Okay. Because, well, you get in touch with your family, with people at work, and so on. So it's not very different from one place to the other. Well, I'm saying it does not. But, so most human society have the number of infectious contacts depending only on the number of contacts, and this is due to the social structure of human society, where you have contacts with your friends, with your family, with people that work with you or at school. There can be effects like, okay, for diseases that affect mainly children that are in schools, and then you have very strong agglomeration in the schools. There could be this effect. There could be the subway effect. When big cities have subways, you get more, depending there more or less on what kind of disease we are talking about. And because, for instance, the subway effect is only important for like flu, because flu you are still going around the city. Other diseases, it will be not in the metro, in the subway anyhow. Okay, so these effects can be maybe even calculated, but in general, the idea that diseases do not dynamics is frequency dependent comes from the fact that the number of infectious contacts we have is more or less the same due to the society that we live. Okay? Therefore, the case where this is not true is, for instance, for diseases, say, in plants or in certain animals that have no social structure. Okay? So then there's a difference. Okay? So epidemics in plants clearly have a density dynamics, okay? Because then the number of contacts, if you have close packed individuals and or less packed in the, situations, then there will be a difference. So disease epidemics in plants have a difference. And also in animals. Okay? If you have a high density, that's typically cases like cattle, which are managed. Okay? The density can be very different according to how these animals are managed. Then you can have epidemics that are more likely to occur when you have a closer contact between the animals. So then you have this situation here is not anymore true. You have to somehow have a better guess about R, okay? The dependence on the size of the population. Okay? So this is a fact that is usually most of the books that you get on epidemic modeling, introduction to epidemic modeling, do not mention this fact, and actually this is a very important fact. Okay? Well, so continue. Now let's speed up the math, and so somehow these guys will be infected, so they will appear here, but after some time there will be a rate of removal of individuals which will not be any more infective and will become removed, recovered. Okay? That's the SIR, basic SIR model. 3 equations, 3 unknowns. Well, this is nice, but if you also remember S plus I plus R is a constant, okay? Means that I can always eliminate one of them and keep only 2 of them, okay? So this is actually a system of 2 ordinary differential equations, which is what we know how to handle, okay? Now, okay, let's study these equations, but now, this is important. Before you go on, and this is also for your group works, before you go on and let's study everything about the model, okay? You better have first a question that you want to answer with the model, okay? So, okay, obviously you can integrate this numerically and so on, but let's go with more caution here. So, here are the equations, but the question we want to answer is the following. Say at a time t equal to 0, you have a certain number of infected, susceptible individuals, a certain number of infective individuals, and let's say this is the start of the epidemic, then no recovered. Okay, This is not essential. You could have also. It's just simplified calculations. Okay. This is the idea that I have here a situation where I have a population of susceptible people, and a certain number of infected individuals are introduced into population, and this is my time t equal to 0, the start of everything. So my question is, given that we know all these parameters and so on, will there an epidemic or not? Okay, this is the question. I have a population of susceptible people, a certain number of infected people are introduced, and I want to know, epidemic or not epidemic? Because and so what is epidemic? And mathematically in this case is the number of infective people increases. So I want to know if the number of infected people increases. Now obviously you have people arriving at the very first moment. Obviously you have a more stochastic situation. It's not well modeled by this. But the idea is that I will say I have an epidemic if the number of infective increases and number susceptible decreases. Okay, that's the easiest approach to what is an epidemic in such a model. Right, this is the idea. Okay, so we will say this here. This is what we want to know. Okay, so now we have a precise question. We are not saying I just want the solutions of my model. I don't want to study the fixed points for the time being and so on. I just want to know if this is a very practical question. Okay, because you see this is an important question, because if you know this means that if you know that a certain number of infected people are introduced, but you don't have an epidemic, this is nice. Okay. But if you know that there will be an epidemic, then you turn on your red lights, okay? It means that the population can be invaded by the pathogen, okay? That there can be an epidemic, okay? So you better be sure that even the situation that you want is, even if there is an introduction of a certain pathogen, it will not spread to the population. Okay, so this is called herd immunity. Okay, so it's not everybody immune, but means that there's no epidemic. Okay, so this is a practical question, and in order to do this, you need a small piece of mathematical analysis here. And this is the following. So, at this point of time t equal to 0, you have this first equation there. Okay, so all of the variables are taken at time equal to 0. Okay, so I can calculate at time equals 0 that the derivative di dt, let me write this somewhere. Gi dt at time t equal to 0 is just r s0 I0 minus a I0, which is I0 times R S0 minus A. So easy. If R S0 minus A is smaller than 0, no epidemic. Okay. That's good. Okay, but now we want to know if on the other hand, then okay, this is not a good way. Okay, let's start better. This here that means that this function is is positive, means that the number of infected individuals increases, which is our definition of epidemic. Now, if, so just to be more mathematically sound, okay, so so if in the first case, okay, where this is negative at the initial time, I should show that it will be always negative, because we want to know if there's an epidemic if the number of infected individuals increases at a certain time. Here we are also only calculating this at the time 0. Okay? So it's not difficult to show that if this relation here with a inverted smaller than 0 means that the initial rate of change of number of infected individuals is negative at time 0, then it will be at every other time. This is just by noticing that the number of susceptibles can never increase, because it's always a negative term here. Therefore, S is strictly smaller than S0. So F0 is smaller than A over R. Then S is also smaller than A over R, which comes from there. And therefore, you can show that dIdt is always smaller than 0, and there's no epidemic. So, at the end of the day, what we get is that this inequality here is epidemic, or if it's smaller than 0, no epidemic, which can be rewritten as R S0 over A larger than 1 epidemic, and if smaller than 1, no epidemic. And this is called R0. So, without solving anything, just looking at the equations, we get a condition for the existence of an epidemic in this model. If this model is good for a certain disease, then this is a good result. R0 is called the basic reproductive ratio, and it is the essential information that is used by people in epidemiology. So, is this already maybe something useful? Okay. Let me see. Okay, no, yeah. Oh, not back. So this can be useful, yes. Let us look at the meaning of the constants that compose the R0. Yeah. So this is a marginal case, but you know, again, being exactly equal to 1 corresponds to what people say is a fine-tuning of constants. Okay, assumes that you have exact knowledge of everything to infinite precision. Therefore, this is never really true being 1. It can be near 1, but will be larger or smaller. Okay, so just 1 point. Okay. Mathematically, this will say that, well, this is 0 times 0, but, well, I don't know the full result mathematically, but usually you don't look at cases which are only non-generic cases. Yeah. So this result is actually useful, because if you look at the constants, 1 over A is, if you look here, and you do some dimensional analysis, okay, you have population over time here. Therefore, this guy also has to be population over time. Therefore, the dimensions of A is time to minus 1, or 1 over time. Okay? Therefore, 1 over A has dimensions of time. It sets the time scale. And if you for a moment forget about this, this is related to the typical time scale for recovery, because this means that the population will decay from infective to recovered with a time scale corresponding to 1 over A, which says more or less this is connected to the recovery time of this infection. So, if A is smaller, means that the time scale is large, okay? So, means that it's more likely to have R0 larger than 1. Okay? You stay infective for a longer period, therefore this can produce more easily one epidemic. That's okay, good result. If you have a shorter epidemic, which means that A is large, then R0 tends to be smaller. Okay? So this reduces the R0, and the probability of having an epidemic is smaller. Very good. Now, this already gives you a practical thing. So, if I want to, say, manage an epidemic, maybe I cannot avoid it, but I want to manage. Maybe I can take public health measures that could maybe influence this typical recovery time. Okay? Anybody can give me a guess about what can I do in order to have the recovery time smaller? Treat people, yeah. So one thing is treat people, okay? So treat people can be important not only for the person that is being treated, but has an importance at the epidemiological level. If you are able to treat people, then you can reduce the value of R0 and have a lower probability of having an epidemic. Another thing is, okay, I could also say, well, I could maybe consider that this is the time to go from infected to recovered. I could also isolate these people, therefore they are not more infectious, because there's nobody they can transmit to, okay? So quarantine also affects this, okay? So, and what's also interesting is that R measures the tax of transfer tax of susceptibles to infected. Okay, here. Okay, if you are a large R, means that the effect of say one infective on this time derivative is larger. Okay, if you have a small R, means that the effect of an individual that's infected has a smaller effect on the derivative here. So large R's will produce higher R0, right? Which is obviously also something that is connected to our intuition. Okay? It also can be thought there can be measures of public health which have effect on R, essentially is to isolate people in order not to have contacts. Okay, this means that the rate of transfer from infective to of susceptible to infective will be lower because there are less contacts. So this is a way of saying, okay, let's lower the value of R. If you are in a very dangerous situation, for instance, you could say, okay, no public gatherings because you have too much contacts. Like, okay, close the schools. Sometimes this happens. Schools were closed. Okay, this is lowering the infectious rate. Okay? And or quarantine is also a way. Okay? So, and well, also, I mean, the larger S0. R0 would be larger. Okay. If you have more susceptibles, there are more chances to occur an epidemic because there are more people that can be infected by an initial number of infectious people. Okay? So this also gives you some idea about public health measures. What does it say? I want a smaller S0. Well, you know, there's one way that we don't want, which is to kill people. S0 would be smaller, but what can you do is immunization, okay? Vaccines. Okay? So this means that the people is not any more susceptible. Okay? So the pool of people that enters here, okay, is everybody is in principle susceptible. If you have immunization, there is a certain percentage of people that are not in the patients. They are out of the scenario. Okay? In practice, you have, in order to use this result also, sometimes you have difficulties in knowing exactly the pool of people that are being considered. I will make a final comment about this later. So very good. So, okay, one further thing is, okay, now, yeah. Oh, I have made maybe something. Yeah, R0 here is not R at time 0. It is just a new. It's not a parameter. It's a parameter, a composition of parameters. Yeah. Yeah, sure. This is enough. Okay, this is equivalent. Why? There's a reason. Okay? The reason is not connected to SIR model. There are many other models because you can see that they are very simple model. You can have waning immunity, the people from R going to S. You can have vector-borne disease and so on, a lot of things, okay? But it's possible, at all of these new models, there is something which is similar to this R0. And actually, what you can show is that the condition of having or not an epidemic is usually taken mathematically. You have a susceptible population, you introduce a very small number of infected individuals, and then you want to know if they increase or not. This corresponds to the study of the stability of the disease-free equilibrium, which is everybody is susceptible, no infective, no recovers. Okay, so this is usually a solution. Then you want to know the stability of this fixed point, and this you can do for models which are much larger than this. And it always gives you some condition that is of this kind. So R0 is a way of unifying all these different expressions, and so that people take what's the R0 of the epidemic of, I don't know, Zika in Ecuador, so they can have some comparison. So because it's a non-dimensional value. Okay? Yeah, it's a common practice. Okay, it's not mandatory, but in the context of comparing different models, this is usually an easy way to compare models and the chances of having epidemics and so on. Okay, so the phase place of these equations can be shown. This is a numerical integration, and here you have it. You have one axis is S, the other one is I. As R is not important because R can be calculated from the total number of individuals plus S plus I. So this is called a planar system. And you have this line here, which is S plus I equal to N. Okay? So your initial conditions are always there. Okay? And, well, if you start at a certain point here, then always you see here on the right hand side, right part, is you have an increase of infection of effective individuals. Only in the upper part you decrease directly. But what is interesting here is the typical curves where you see the evolution of epidemic, which is restricted to be on one of those curves. So this trajectory has some increase of number effective. It starts here on the right hand side. It increases, but then it decreases. Okay, and then it goes to I goes to 0. SIR model predicts that epidemics go away, increase but then decrease. Right? So this is because this connects us with observation about real epidemics. Moreover, you see that at the end of the epidemic, which is those points here near the 0, the S is not 0. Means that there are still some susceptible individuals have not been in contact with the disease. They're still susceptible. Therefore, the population has not all of the people have not been infected. There is a number of individuals that are not infected at the end. This is also nice. Means that the typical epidemic of this kind of disease that can be modeled by SIR is it has a typical time scale. It increases and then it decreases, and the number of infected go to 0, and you get also that the number of susceptibles at the end of an epidemic is not 0, meaning not everybody was infected. So nice. This model has a lot of very simple model has a lot of realistic aspects. Okay? So you can actually calculate what people call the final size of the epidemic, which is what? It's calculating the number of recovered persons at a very large time. Okay? In this model, once you are recovered, you have immunity. You do not become susceptible. Therefore, at the end of the epidemic, which mathematically is t going to infinity, there will be a certain number of persons that are recovered, and by definition, end of the epidemic is I equal to 0. Okay? So I will know all of these guys have been infected, because the only way to be recovered is having been infected before. Therefore, the final size of the epidemic, the number of persons that have been infected and then recovered, gives you the size of the epidemic, and 1 minus R infinity gives you the number of susceptibles that have escaped the disease. Okay? So you can calculate this actually by doing this kind of small tricks. Divide one equation by the other, okay? Like this. Divide this one through this one. So you get dsgr, okay? And it means that the number of susceptibles in terms of the number of recovered are given by this first equation here. And for large time, I goes to 0. Therefore, S infinity plus R infinity is equal to N, which gives you an equation for N minus R infinity is equal to S0 times this exponential, which is a transcendental equation determining R0, R infinity, okay? So you can calculate this numerically, okay? Transcendental equation, there's no analytical solution. So you can calculate from the SIR model, again, without knowing the solution, how will be the size of the epidemic, okay? Which is nice. Well, and here's the solution. I didn't show you any solution of the SIR model, but this is the solution. This is the number of susceptibles, and this is the number of infective. You see the number of infective starts growing and then reaches a maximum and then decays. And the number of susceptible always decays. This is done with data from, this is historically, I mean, it's a textbook example from a boarding school and in UK with the epidemics of flu. Okay? It's really a closed system. It's kind of almost an ideal system. A boarding school, nobody. So it's the curves has been obtained numerically integrating the SIR model and so on. Okay. So very nice. What can we do else? Okay. We can do a lot of things, creating new models. So I won't go into the details of lots of models because, well, this is it's quite long. But the way to think about this is, it's always this kind of compartmental modeling. Then you say, for instance, I can have a model which is SIRS, meaning that I have susceptibles, infective, recovered, but the recovered can be susceptible again. So there is a typical time connected to your immunity. When you lose immunity, or you have a waning immunity, then you are susceptible again. So you can have models with this, and you can guess. I mean, this will not be very difficult. You just have some transfer from here to here. Okay? Easy. New compartments can also be introduced by creating a new compartment which usually goes here, which is susceptible, exposed, but not infectious. Then the infectious, then the recovered. And then you can also say, okay, recovered goes back here or whatever. You can have a fraction of exposed that actually don't get infective. All variation you want, but the way of writing the models will be just taking all of these compartments into account. You would write a D, the T here, and then you say, okay, some of them go to infective, some of them go back to susceptibles or go directly to recovered. All of this will depend on the nature of your disease and the knowledge you have about it. Other models comprise things like, there's one important case, which if you download this from the web page of the school, you can read this. I won't do this here because I don't want to go very late today. One way is also saying, I have a constant population, but I have a certain number of births and death. There's a death rate and a birth rate, and they equilibrate one another, so it's the same. The birth rate and the death rate are the same. So then this will have a different dynamics because the number of susceptibles can have the equation for the susceptibles has a term that injects susceptibles in the system because people that are the newborns are all of them susceptible. Okay? So what you do is you add a mortality, which is the mu, right? And then you add a term where susceptibles are being born. Okay? So this dynamic gives you, well, I don't go into the details here, but gives you this. Gives you oscillations of decaying amplitude, but contrary to the SIR model, without this effect, which is called vital dynamics. Okay? Without vital dynamics, you don't have oscillations, and you have always the extinction of the disease. In this case, you have oscillations, and you go through a non-zero value of infected people at the end, which means that the epidemic is now an endemic state. Okay, so you can also process all the information that, like the calculations I've made here, like calculating R0, calculating other parameters of the epidemic for the model SIR with vital dynamics, which gives you this kind of solution. Okay? Oscillation and decay. Okay? Actually, this SIRS model, where the susceptibles, the number of the recovered have a certain time after which they lose the immunity, gives you also oscillations decaying to an endemic state. Okay? So you have. So this is also nice because, you see, with small modifications of the model, I can also explain not only the real epidemic, but I can show that an epidemic can have as a final state an endemic state. Right? But what else? Well, I can also consider vector-borne diseases. In this case, I have the humans, and I have also a new population, which is the vector, like the mosquitoes, for instance, of malaria or dengue, all of these things. Okay, so you can put susceptibles, infected, and recovered for humans. Then you put susceptible and infected for your mosquito. Mosquito never recovers; there's no recovery. And then you write down models like this, where the number of susceptibles of humans will appear here, but the infective is not the number of humans which are infected, but the number of mosquitoes that are infected. Okay? So then obviously you get a larger system of equations, but it's not difficult to calculate, even analytically, at least the R0, define it as the condition such that a disease-free equilibrium becomes unstable. And so this can all be done. And this is more or less the big view of models in epidemiology. Right? You can also honestly do very different things like stochastic models when you have a small number of individuals and so on. But we can also ask ourselves that, okay, now what about data? Okay? Can we compare models with data? Well, sure you can. Okay? Sure you can, but there are some tricky things. First is, let's be practical. Being practical is I want to know R0. Okay? Because a larger R0 means that that will have a larger epidemic also. So, and how long it will take for the epidemic to go, all of this will be in the R0. And so if you want to use fitting the data, this means that you have to have the solution for the number of infective. I mean, you want to fit the solution of your equations to the curve given the number of infected people over time. Say something like this. Okay? Number of infected is small, then increases, then decreases, something like this. Okay? Well, but this means that you have to wait the epidemic to come and to go and then fit the data. But then your public health officials will say, come on, I want to know R0 immediately. I don't want this. I mean, what's the use of R0 if I can do anything because the epidemic is already there and it even went away. So I don't want you to fit all this data. I just want to know R0 and at the very beginning of the epidemic. That's the practical thing for public health measures. Okay, knowing R0 at the beginning, so that I can say, okay, I have a more drastic situation or a milder situation. This is, and actually, yes, you can do this for at least if you have a simple epidemic, which is well described by R0, by SIR model, because there's something nice. Let's look at the very beginning of the epidemic, and let's look at this equation. Okay? This gives you the number of infected individuals over time. Now, at the very beginning, there are only a few individuals that have been infected. Okay? This means that this S here, at the very beginning of the epidemic, is very close to S0, which is the initial number of susceptible individuals, which is something that usually is the whole population, something I know. So I will say that di dt is well approximated at the beginning of the epidemic by something which is S0 I minus I, which is just R S0 minus A times I. Therefore, for small times I, the initial phase is proportional to some initial number of infective times E to R S0 minus A times T. Exponential increase of number of infective at the very beginning of the epidemic. But this is nice, because here, as you see, this you can write as if you remember the definition of R0, that was just this R S0 over A minus 1 times A times T. Okay, this is R0. Therefore, if I know, this is usually something I know, that's the typical time to for a patient to recover, and this is more or less fixed for each disease. Okay? So this I know. This is R0. Okay? Therefore, if I make a log-log plot, okay, logarithm of I time on t here, okay, get logarithm of this is equal to this. There will be a logarithm of I0 here, and this will be just a line, okay? So the inclination of the line will give you R0 minus 1, okay? Therefore, you can calculate R0 at the very beginning of the epidemic. This is really great, and this is used, okay? Well, good, very nice. So, what is the problem with this idea? Well, the problem is, at the very beginning of the epidemic, maybe you don't even know if there the number of cases because it's very, very few people. So you can have many problems. Okay, depends on the kind of disease. If the disease takes time to affect the person, okay, and then you have a problem with how is your public health service? Is there rapid notification or not? Okay. How is usually epidemiological notification? Okay, so a person goes to the doctor and has a diagnosis. Oh, you have malaria. Okay, then there's a process of notifying the public health service, which takes some time. Okay, and it takes some time, and then all the data in epidemiology are always given by weeks. Okay, so the time scale is always weeks. So you don't know the number. If a typical survey of epidemiological survey will not give you the number of infected every day. Will give you the number of infected or the new infected every week, which is okay. So there's a time scale. And if the epidemic grows rapidly, this time scale may be such that when you get the information that could lead you to obtain R0 from here, you are not anymore at the very start. And if you're not at the very beginning here, at this point of then this approximation taken as like S0, which is what allows us to do the calculation, is not valid anymore. Therefore, whoop, you're lost. Okay, you have to do something else. Then this is usually testing people and so on. Yeah. But anyhow, it's still a possibility, and it's done when you get notifications of diseases that are. It's very useful in diseases that are really easily to have the diagnosis, and notification is also rapid. Okay? So you see how important it is also that you have good structure of your public health service. That having this on a computer and not on a piece of paper will really give you the possibility to detect things earlier. And the earlier you detect an epidemic, the better. Okay? So this is actually that if you talk to people that do modeling in epidemiology, people that from public health that are really in contact with data and to models, and one of the important things is always to detect the epidemic early, and this is a problem usually. Okay, there's a famous case like influenza. Yeah, I know a guy that actually is the guy that models influenza in Brazil, works with the Ministry of Health and so on, public health. And the point is, influenza is a nightmare, because influenza is not of a mandatory notification. Okay, and most people don't even go to the doctor. Okay, because do you go to the doctor every time you have a flu? No, only if you have a very extreme case. And usually you say, okay, I take some aspirin and tomorrow I'm okay. So it's an epidemic that goes unnoticed. But actually a lot of people die of influenza. Newborns and aging people over 70, 80 years old. So it's important to know the epidemic, but it's kind of flying under the radar, right? So it's not nothing that you can really get easily the data. So how do people work with this? Okay, so people work with severe cases, because severe cases is when the person goes to the hospital and sometimes get even to spend some time in the hospital, and this is something that's on records. So this is data that is used for modeling of influenza, severe cases. This is always, all of this is very messy in epidemiology, okay? Because usually you have that. I mean, if you have a private hospital, maybe he doesn't want to report. It's not mandatory, so usually you use the public hospitals. Okay? And, well, then you have problems, and there are areas where there are much more public hospitals than other ones. And things which are like, in practice, is like, the data sometimes is has just say weeks without any data. Okay, this happens because it's not well organized, at least here in Brazil or in Latin America in general, and many places actually. Which is just that, say, there's usually one person that just the person that uploads this into the system, so on, and take vacations. Nobody does it. Okay, so you just don't have the data. It's just really a pity. Okay, what people do, for instance, in the United States, what is done is most of with private hospitals is they pay the hospital to report every week. So the hospitals somehow manage to report on, otherwise it's not paid. Okay, so paying people solves the thing, but just waiting for the hospitals to cooperate is also messy. It's not, and this is only to detect the severe cases. So you see, it's very difficult to have data for influenza, for instance. Okay, so then there are things that are reported, like malaria, dengue, this kind of things. They are always reported. So you have a better situation, but well, still it's not very easy to. And then there are things like, I saw a paper 1 year ago, more or less, that was modeling Zika in Colombia, okay? And trying to calculate R0 and fitting models and so on. Okay, nice idea, so on. But it didn't work, actually. The paper was eventually published, but shouldn't have. Because you had something like increase. So this is obviously not SIR. Okay? So you say, why? Well, this is strange. So what did the paper? What's the approach? Let's take the total number of people in Colombia and say the incidence of the disease, right? But well, this is not a closed population, and Colombia is a large country, okay? So what you are seeing here is waves of different cities which have been aggregated into one country, okay? So from the point of, so you have an epidemic, if you go, I don't know, from one city, you go to Bogota, or you go to other cities, then they are not having the epidemic at the same time, because it propagates. So if you aggregate data for whole Colombia, you get a mess. Okay, you get a mess because you have different. You have those, spatial dynamics that is very important, and you are not taking this into account. So what you should do in this case is let's fix on one city, or maybe we can have several cities, but you study each of the cities separately, and then you try to obtain the epidemic curves, and then try to calculate R0 for each of the cities, and maybe they are more or less similar or not. Okay, so that's really a pity. So this same paper actually did the same thing for Guyana and for El Salvador. And the model actually worked well for El Salvador. Right? But this is probably because, well, El Salvador is a small country, that this corresponds to not so large distances, so that you don't have this kind of waves of infection going from one city to the other. You're aggregating this on one country was still okay. Yeah? And Guyana gives also something very strange result. I don't like very high R0. I mean, more than Ebola. So okay.
Also, looking at the single epidemic in a city,
yeah,
and then classifying it by the social economic status.
Sure.
And you also see something like that, like start with the poorest people.
Sure. In many cases, depending on the epidemic, on the kind of disease that has the impact of the social conditions, sanitation, access to public health services, all of this have a very big importance on R0. But I mean, this you have to take care with the disease. For flu, this is not true. Flu, I mean, rich people get flu more or less like poor people, except for immunization. But this is still a very small part of the population.
Right. But then, talking about the subway effect.
Uh-huh.
That usually poor people use massive transport systems.
Yeah, it's true. It's true that I mean, if you are rich, you are more likely to have money to take preventive actions. Okay, that's true. But most of the time, this social aspect is more important for diseases that are not transmitted directly between people, but go through the environment. So the classic case is cholera. Cholera, to write a model for cholera, it's usually an SIR model plus an aquatic phase for the Vibrio cholera. So you have to take into the aquatic phase. So, and this has to do with sanitation usually. Okay, having sanitation means you don't get cholera. Okay, and that's actually the way that cholera disappeared in large parts of the world, and Europe, and there was a lot of cholera in the Mediterranean area at the beginning of the 20th century. Right? So how it just disappeared, it went away. It's sanitation. It's the same thing. There's no epidemic. I know a person also that has written a model for cholera and applied to Brazil and so on. And I was talking to this person, and actually, what turns out that she said, well, you know, I don't work anymore with cholera because cholera disappeared from Brazil as an epidemic problem, public health problem. So, how was the strategy? Well, nobody did anything, actually. But well, this has come from urbanization, sanitation, and so on. Don't have anymore the possibility of having the aquatic phase. Therefore, okay, cholera disappeared. Bye-bye. Good. Okay. So this is typical effect of environmental conditions. Yeah.
Is there any model that takes into account, for example, electrical changes behavior?
You can do very nice things which are more recent works. Okay, because this is old. I mean, this SIR model is 100 years old. But you can introduce behavior here, and you can actually couple epidemic models with game theory models, where people have to take decisions. For instance, will I vaccinate or not? So you can put two strategies, vaccinate or not vaccinate. You have a payoff matrix, and then you have the equations of game theory coupled to this. This is nice. So you can take into account. Sure, you can have two streams of the disease. You can have two different diseases that maybe can have competition between diseases. Okay, sometimes you have a person has one disease, and then it doesn't get the other one. It's like has been colonized first by one of the diseases, and then gives you immunity to the other diseases. Okay. And then, well, then you have like things also with the strains of dengue. There are 4 kinds of dengue. Okay? So then they have to consider cross immunity between one and the other. Lots of things. Hyperinfection. It's like if I had, this is known, if I already had dengue of a certain strain, if I get dengue from another strain later, this can have a very high, I mean, a very strong effect. You can get hemorrhagic dengue or danger of life and so on. So all of this can be modeled. Then you can also model viral load in a person. It can be important. It's important for HIV. HIV is not eradicated, but people having very low so because here we are characterizing a person has or not the disease, okay? You're infective or not, or you're susceptible, okay? But could be also that you may be infected, but the infectivity depends on the viral load, okay? And this can be taken into account in models. HIV is a typical case where this is important to take into account. No. Actually, I don't know exactly. I can because the person tried to fit a simple model on this and say it doesn't work, but obviously it doesn't work. But what can be here is that you have different cities at different times having could be a wave of but can also be different new introductions. You have the epidemic developing, but then somehow it's not traveling for other city, but some city, there are new cases coming for introduction through immigration. Can be anything. Okay? No, this is usually, well, that's the topic from tomorrow's. Thank you. It's just diffusion. Okay, but tomorrow it's back to ecology, but can be also done in epidemics. So spatial epidemic dynamics is also a mess. This is very, very complicated thing because what you would do would think at first is that you have an introduction and then you spread the epidemic. Okay, so this is sometimes true on very large scale. If you look for plague in Europe in 14th century or even in the 17th century, and you get the reports of where you have an epidemic of plague. It's really coming and expanding like a wave. Okay, this is what happens sometimes, but in today's world, this is not anymore usually the case. So the travel, because disease take planes. Okay, so they travel by plane. So you need to take into account that depending on the disease, if it's obviously if it's Ebola does not travel on the planes because people get very sick or even die. Okay? But other things travel by planes, and then you have to take into account that the movement goes at a large scale. The disease spreads through a network of connections, which are usually networks of air traffic. Okay? And At a lower, at a smaller scale, obviously there's no planes. And you have to take into account even, I know, roads, or a very small scale. Usually, then you have a more a situation where space is not so important, and one city usually is not so important. Yeah. And just to mention, I say about eradication. One thing that's very difficult also is to achieve eradication. All these models here, in principle, they have states, can have final states where the epidemic is went away, but obviously, and this is called the epidemic is extinct, which means this precise epidemic is extinct. Disease eradication is something else. Okay, this is connected to really have no place in the world with the disease. And so there's only one eradicated human disease, which is smallpox. Okay? Smallpox has been eradicated. It's a very big success of the World Health Organization. Eradication of smallpox. And there's one that is almost eradicated, which is the Guinea worm disease, which is a worm that goes into your body and so on. And it's only present in Chad and Ethiopia. Okay? So, which is related to really poor situation, no sanitation and so on, but this is almost eradicated. And this is this worm that you see it sometimes when you have a doctor, medicine has a kind of logo, okay, which is something like something like this with a worm here. Okay, this is the symbol of medicine, and this is actually the worm. It's the Guinea worm, which has the only way to take the worm out of your body is somehow having something, and very bad. In taking it. It's 2 meters, 3 meters worm. It's horrible. At least it's been eradicated. So thank you very much. I mean, if you have more questions or comments, you can do it. I didn't hear you. You can help? Yeah, okay. Yeah, there are always situations like that. That's why people take an eradication. It's not that you don't have any case anymore, but you don't have any case over the next, over 5 or 10 years. And then you say, okay, then it's not the problem of diagnosis. Anything else, people? So, I wish you a very good afternoon with talk, with a lot of work. Today, we have an evening session. At the evening session, we will ask you will be allowed to ask any question you want. Okay? In principle, I try to answer, but I don't know, there's Paul, there are monitors, and maybe you know how to answer. Okay? Any question you want about anything. Okay? But I know most of people are shy. Okay? So people don't raise their hands. So if this proposal were like, come here and ask questions, it would be 15-minute session. But that's why you can pose your question on a small sheet of paper, and my suggestion is that if you come for coffee break around 4, there will be boxes here, you put it there. I mean, can do it anytime you want. I will provide some special sheets of papers which are nice with the logo of Bestiario and so on. Then you can have this, and you write your questions, and please, really do it. We have 60 people here. Let's have at least 60 questions, okay? Good? So this is at 6. Yeah, at 6 you get this. In the afternoon, now, we are on Thursday. You are near to your presentation, so you better now come to a decision of what model are you working on, what are the premises, what are hypotheses, what effects go into the model, which effects don't go in the model. You write the model, you have to usually run the code and so on. So today is a very important day. I mean, if you arrive on Friday without model, we would be kind of crisis, okay? So think about it. Thank you very much.
Quedamos con el producto colombiano y la chica española ahí en 15 minutos. Yo regresé.